Okay, I thought I would go into a little bit of depth on how M-PHY configures itself. This is kind of an interesting slide. The colors of the actions match the arrows here. So when the link powers up, the local protocol checks the capabilities of that PHY and also receives the capabilities of the remote PHY, which you can see with both arrows, both green arrows coming back to the local one. And so it looks at those. There's actually an appendix in the back of the M-PHY which describes how you would look at the different attributes of each side and how you would select which one, or the best way to configure the link based on the attributes you're going to get from both sides. So the protocol then, based on this information, decides on the operational protocol, or the operational profile. Then that profile request is sent from the local PHY via the protocol layer to the remote, and you can see that with the purple. So that we're configuring both the PHY on the local side as well as the PHY on the local side, or on the remote side, with the information the protocol has decided on how this link should operate together. Then they go through, if you'll remember the state map, it would go through a line config cycle or through an RCT that will activate the change. And in addition to this, you can see I've added in this electrical to optical media converters. Those can be configured by flushing the configuration data during the line config cycle. So another unique feature of M-PHY is that it's prepared to have media converters in the line from the beginning. So for instance, if you have a reach that exceeds the physical layer in terms of distance, you can convert to optical, or you can have just another electrical link that will extend the range of M-PHY. Alrighty. Let me see. Now, another thing I wanted to talk about, even though the interconnects are, the specification is informative only in M-PHY, I wanted to take a look at some of the ways that M-PHY is anticipated to be used. What's unique about the phone and the tablet is it's such a small form factor that you have extremely high density interconnects, different from your PC. And also probably a lot of vias. You'll have a lot of layer transition to get in and out of. The SoC is a very small space, and you've got to get a lot of signals in and a lot of signals back out. So even though the distances may be short, the electrical constraints are actually pretty challenging. But we think that M-PHY will handle certainly the HDI with multiple vias. Now another concept that we've seen sometimes is to have boards that are stacked through a connector. Again, I referred to the optical one where you might have at the edge of the one board a media converter which converts, say, perhaps to optical to go some distance to another board. And then I think the one that's probably most prevalent these days is the multi-layer bend once flex. In other words, instead of a clamshell where you're always opening and closing it, this is something like you would connect, say, from a motherboard to a display, where you're really taking that flexible cable, you're bending it once to put it in the case, and then you're done. Let me see. What else do we have here? And I wanted to talk for a second about the M-PHY specification roadmap. As we know right now, the version 1.0 is out. That goes at 1.45 gigabits per second. It supports high-speed gear 1 and the PWM gears 0 through 3. And also, what we like to do with these specs is give a sort of a foreshadowing of what the next speed would be. And so this allows for contributors to build test silicon ahead of time, such that as we actually define the next gear, we can have data from the test silicon in industry to validate whether we've done the right thing in terms of the specifications going forward. So we have this little sanity check built in. pretty soon, I would believe, you know, within weeks, we'll have the version 2.0 available that will be adopted, which has adds the second high-speed gear, adds a few more PWM gears, and then gives again a provisional bandwidth hint into high-speed gear 3 and PWM gear 6 and 7. The people that use high-speed gear 1, DigRF, that's a interface that goes between the digital baseband and the RFIC within a modem. Other people that are have used it are UFS through JEDEC, and it's also part of the LLI and the SSIC spec. With the Gear 2 that's coming out very soon, we should continue with UFS, LLI, and SSIC, and all of a sudden it starts becoming of interest to cameras. So we see the CSI adopting it. Now, you'll see the purple line for DigRF stops at Gear 2. That doesn't mean that the development stops there. It's just at the current time, they see a use for the version 2, but they're not sure about the version 3 and going forward. So one of the activities we're going to have this week is to go sit down with them and work out the roadmap going forward. The high-speed Gear 3, we would like to see that. The pacing here you can see is what I like to call a gear a year. So we'll have the version 3 hopefully sometime next year at this time. That will include high-speed 1, 2, and 3, as well as all of the PWM gears, with provisional, again, hints forward-looking to, as Rick mentioned earlier in the TSG report, the Gear 4, which we would think would happen the year after that, at a rate of up to 11.6 gigabits per second. Let me see what else I have here. Okay, well, since I'm the guy that's standing between you and your break, I guess it's okay that this went faster than I thought it would. Are there any questions before we go to the break? Don't be shy.
Can I have one question?
Yeah.
So was that VPAT, the power level that you showed, the power consumption?
Was it at?
The battery voltage.
I'm sorry, still
the battery voltage.
Oh.
So you had like, I guess 10 microwatts?
Yes.
So.
Yes. Was it at the battery voltage?
Yeah.
I would presume so, although with test silicon, it's always hard to tell the context that they made the measurements in. Okay. But nice question, thank you. Anything else?